of modern philosophy of science can be understood through Peircean terms. If you buy into the full package of Peirce, that was the claim. Yeah, so plenty of interesting ideas there, I think.
All right, thank you very much. And with that, I think we're out of questions, and let's move on. So our next speaker will actually still be David Corfield, and he'll be talking about type-theoretic expressivity. So feel free to share your screen, David.
Could I just ask, am I allowed my 6 extra minutes or so? Or is that to people desperate to go?
Oh, sorry?
Is 6 minutes late? Is that a problem if I carry on?
I don't think is anyone in a rush here? Yeah, everyone seems to be enjoying the show, so don't worry.
Very good. Ooh, why is that not moving? Is that moving? Oh, sorry, it's moving. Great. Okay, great. Thanks very much, and thanks to the organisers especially for allowing a philosophy section. Talk about inclusivity. To include philosophers is very kind of you. So something I've been trying to set up in some sense is you talk about act and then tact. I've been trying to set up fact, philosophical applied category theory. So we've had some Peirce. Let's try a new channel. And today I'm going to talk a bit about Robert Brandom, so Pittsburgh philosopher, who's well known for his theory called logical expressivism. And the key question he's trying to answer is what's special about logical vocabulary? What makes something logical rather than not logical? Why is it not going? Oops. Yeah, and a reason to be interested right at the moment is in a few weeks' time, in 17 days' time, he's going to be speaking to the Topos Institute, articulating the structure of reason's logical expressivism. Okay, so there's some ACT interest there, I think driven by Chris Brown. He seems to be getting very interested in Brandon's work. Okay, so here's the argument today. I've got rather a lot of material. It occurs to me, well, normally I'm presenting this, the pathways to interest philosophers in category theory, and here today we're going the opposite direction. So most of the time they don't even know what an adjunction is, or even a category. So a lot of work has to be done. I mean, here I can slide through all that stuff because you know, like the back of your hands, obviously. Okay, so the argument goes like this today. So this logical expressivism developed by Brandom is looking to understand logical vocabulary in terms of what it makes explicit about our ordinary inferential practice. So it's trying to explain why we use common logical connectives, implication, conjunction, negation. So then the thought goes, well, wait a minute, but there are type theories for which these connectives arise just as restrictions of the more general type theoretic constructions. So why can't we give these, or we can, I think we can give these an expressivist reading. In which case, then why not, what's to stop us taking the whole of this type theory as a kind of logic to include at least dependent type theory? And maybe get a little bit less hung up about the vocabulary as such, and to look at certain kind of constructions as just as logical as part of our ordinary inferential practice. Okay, so the first strand of his work is to buy into an idea that's pretty common in the philosophy of logic called inferentialism. So it's kind of grown out of it. It's understood the presentation of logical connectives in terms of introduction and elimination rules. And this sits very nicely with Brandom. Brandom's keen for you to think about the meaning of expressions in terms of if they partake in some assertion that you make, you better be able to give me reasons for making that assertion. I can challenge you on that assertion, and you better tell me why that's reasonable to believe it. And then once you've done that, certain consequences follow. Once you are justified in asserting something, some certain things will follow. And this works absolutely beautifully in the case of logical language, because clearly things like the introduction and elimination rules for things like implication make this pretty plain. I mean, okay, if we're trying to understand the meaning of A implies B, well, it's come from the fact that sort of B follows from A. If B follows from A, then that implies the truth of A implies B. And similarly, what does it mean? What am I committed to? Well, if I have A implies B, and I have A, then clearly I have B. And that's really in some sense all there is to implication. Okay, so we can, there are different ways to do this, but let's just give it a brief category theoretic account of what's going on there. If we're taking the propositions there in the context, when we have a list of them anyway as some kind of conjunction, okay, we can understand them equally in these terms as though there's some adjunction going on between conjunction with A and A implies. Okay, well-known adjunction going on, so that if I have an inference from C and A to B, then I've got an inference from C to A implies B. So the introduction rules are just reflecting the one part of the adjunction there. The elimination rules, they're the co-unit for the co-monad. Okay, so if I come and go with the adjunction, then that's going to create a co-monad, and the co-unit for the co-monad is just the elimination rule. Okay, so this is making logic and category theory sit beautifully together. As Lawvere tells us, logical constructions arise. There are a web of adjunctions, as Lawvere puts it. The tonk there, if anyone knows a little bit of philosophy of logic, some guy at some point suggests, well, why can't I have any old connective? Why can't I have A tonk B? Give you the elimination rule for it, introduction rule for it, and then so chaos ensues because they don't sort of sit nicely with each other. Well, that's because if you set the web of adjunctions up properly, nothing bad will happen to you. You'll get harmony or the computation rule. Okay, and conjunction, so it's right adjoint to duplication. I mean, how much more basic can you have than that? I have a proposition and I kind of just say it twice. With duplication and conjunction is just right adjoint to that. Okay, so the introduction rule is there, and the elimination rule is the co-unit. So similarly, the left adjoint to this duplication is just a disjunction, and now it's the other way around. The junction represents the elimination rule, whereas the introduction rule is the unit of the adjunction. Good. Okay, so this should be resonating all sorts of things, you know, this computational trinitarianism that Bob Harper coined at a certain point, I think 2011. There's a bit of a battle going on, just like evil has been removed from the NLab after many years, and there's not certain debates. Seems like trinitarianism is frowned upon a little bit. It gets called trilogy at the moment, but although I think it makes more sense to call it trinitarianism, but still. Okay, so it has these three sides to it. We're trying to unite computation, logic, and category theory. So I've been talking about the logic and the category theory bit as wedded. What about the computation? Well, why not? Right, there are different ways to cash out what you meant by computation here, but in a certain kind of broad sense, you could make it fit with this thing that Brandon's trying to do, this expressivism. So let's give that a go. What is this expressivism? So the expressive role, Brandom tells us, that distinguishes logical vocabulary is to make explicit the inferential relations that articulate the semantic contents of the concepts expressed by the use of ordinary non-logical vocabulary. So in a sense, you sort of provide almost a just so story. You sort of imagine some people who don't have these words. They don't have the word for implies, say. What would life be like? And then suddenly along comes somebody says, oh, we could have a special word, implies, and look how that makes life easier for us. It's made explicit stuff we already did, because we already had people uttering a statement A and then a little bit later uttering the statement B, and we all kind of nodded, oh, yeah. But now they've made it explicit with the notion of implication. I can now wonder about the truth of A implies B. Okay. And in a sense, this is what the intuitionistic conditional does, he tells us. It's letting us assert that there's a procedure from turning an argument for the premise of an inference into an argument for the conclusion. And similarly, if I'm thinking, what's the role of and, the logical and? Okay, well, again, if you didn't have that and, you imagine your people going A, B, and then after a time C. Well, did that C follow from A and B? When we have that and made explicit, it makes explicit precisely the practice of co-asserting to propositions. Okay, but these implies and, of course, these are just projections down from some higher sort of type-theoretic constructions. Okay, so drawing on a little bit of something Mike Schulman did for us a while ago on the Category Cafe, he was telling us about these what he calls these three theories. So the first one here is what he calls a simple type theory, where you just have a type on one side and a type on the other. And then he called that, unary type theory. This one he calls a simple type theory, where there's no dependence going on. It's just a list on the left, and then you get a single one on the right. Then we get a kind of first order system, where we get a typed first order system, where we get a series of declarations of variables belonging to certain types. And now we get a second layer of types, really propositions or dependent propositions or predicates, if you like, that depend on these variables that we've introduced, and then also on the other side of the turnstile. And then a little bit higher up the hierarchy, we have a proper dependent type theory. And then he mentions ones, of course, you can put multiple consequence on the right-hand side there. Okay, so seen in a certain light, I mean, the ones that the philosophers are most familiar with would be the third one, the first order logic case, but they typically don't see it in those terms, because they very typically work with an untyped or unityped first order logic, where you don't get these A's and B's and C's. So let's slash those off. You just got a single universe, a single domain. And then because these P's and Q's and R's, they're typically propositions or dependent propositions, i.e. predicates. They typically, they're yes or no, and if we're asserting them to be true, we don't bother inhabiting them with terms, P's and Q's, little P's and Q's and R's and S's. So we'll get rid of that as well. And that's typically what remains. This is first order logic as projected out from dependent type theory. So we can see this at play if we could take the construction in type theory. Dependent function types sometimes get called dependent products, if you know in those terms. Here are the formation, elimination, and introduction rules for this construction. So when you have a type and you have a family of types that depend on that type A, you can construct this dependent function type, where if you've got an element of that type, you can apply it to an element of A, and it generates an element of B of A, and so on and so forth. And there's the introduction rule. So if you play those things out in these reducing them down to the simple cases before, if you play it out in propositional logic where there are no dependent types, that just manifests itself as precisely as the type formation rules for implication. It becomes A implies B. Elimination is just A implies B and A, therefore B, and introduction is just A therefore B, so A implies B is true. If you do it to first order logic, you only have this one domain. Remember, one universe, one non-dependent type, the universe of discourse. So we don't usually bother mentioning that. So it looks like what's left are basically a predicate. B of X is a predicate, and then you would form the proposition for all X B of X. So term introduction then becomes this: if B of X, then for all of X with B of X, and term elimination allows you to substitute a value in there for X. Okay, so from the category theoretic point of view, this is just context extension, if you like. So if you've got a category C, and we're thinking about the slice of the category of C over a particular object A, this is equivalent to what's going on in that process of taking a type in the full category C and seeing it now as a dependent type, a trivially dependent type B, in the context of the category of the type A. So this is this process here, or if you like, it's like sending an object to a projection of A cross B down to A, just the projection onto the first component. And then note, I mean, how if you're giving a kind of expressivist reading to what's going on here, well, what are you doing in that process? I mean, it's a little bit like you were chatting away, you built up a context, and then you're about to declare this new type B. Would it make what difference would it have made if you'd made some little side comment? You'd include an extra thing in the context, something to do with A. Well, if you're never going to use that again, if the X never gets used again, really all you've done is made a little aside. And that should be part of our inferential practice, that if you're chatting away and then you make a little aside about something that you never use again, and then you go on and start concluding something, well, that shouldn't have mattered, that aside. It should be something that just passes. Okay, so again, the story carries on. Dependent function is the right adjoint to this context extension functor. An introduction, the elimination rules work very nicely from the adjunction. and the elimination rule is the co-unit of the co-monad that generated by the adjunction. So that if you think in expressivist terms, well, we had that one already. If we had two propositions, I might want to consider the proposition A implies B to know the truth of this, because then I'll know whether B follows from A or not. Similarly, if I have a predicate B of X, it's worth me considering the proposition for all X B of X. And so similarly, when I have the full dependent type theory, I might want to consider this new type, the type of assignments of one of A's B's to each A in A. If you get hung up, if you want to see, Brandom seems to want the logical language to have appeared. So the first one is clearly the use of the word follows or implies or something like that. And the second is the use of all or every or something like that. Yeah, as it appears in natural language, it would be something like, as we'll see, something like the possessive. There'll be some sort of functional assignment going on. So we've seen the expressivism for the introduction rule already for propositional implication. In the second case, I mean, again, this is part of inferential practice. You can imagine a people that didn't have the notion of for all. You know, what would you do? Well, you'd contemplate the existence of an entity of a certain kind. You'd probably use the indefinite article. Imagine a stranger appears into our terrain. What do we do? We should fear them, says somebody. Okay, if they had available to them the language of for all or all, they could consider the proposition all strangers should be feared. Okay. So that you've made explicit something that was going on in the inferential practice. And so similarly, I think in the full dependent type case, if there is this situation where there's some sort of natural assignment of an element of the type of B of A for any particular A. I mean, often you're going to want to name that thing. You're going to want to provide precisely a term for that thing. If you imagine the type of teams, and then depending on it, the players that play for that team, there's that assignment, that one that plays at the back all the time, the one that sort of is able to use his hands. Oh, right, let's give it a name. That's the goalkeeper or the captain or whatever. But this is just all over the place, isn't it? This is if you think of a plane going along its flight path, I might want to, it could have all sorts of heights at any point along its flight path. And the altitude of the plane along the flight path is a section, a mathematical section, isn't it? These are regular assignments, rules, laws, often indicated by the oval, possessive in some sense, the plane's height, altitude. Okay, and I can tell a similar story, a dual story for a dependent pair. I still get my Fiek rules. I get an adjunction. This is now left adjoint to context extension. It's going to be conjunction for propositional logic. In the first order case, it's amounting to something like the A's which are B's. It's only in the typed case at least. And it looks like I want to truncate that down into there exists an A which is B. This is something I'm frequently going to do. Okay, but it's something again I kind of want in my inferential practice anyway. Because there's a sort of underlying thought here that just intuitively we're kind of dependent type theorists, almost in our everyday speech. And I have a suspicion that's why lean is working so well with Kevin Buzzard as a language to try and take some informal mathematical proofs and turn it into formal mathematics. I think we're just intuitively using something like dependent type theory, certainly in informal maths, and I think in informal language in general. Okay, so we do this all the time. We want to pair things. We want to pair, say, authors and their books. And then we can do things with that type. We can do some inference from that type. We can bundle them together, authors and their books, in that kind of way. And again, if you want the representation in vocabulary for that thing, you might say and its, an author and its, or an author and their book, something of that kind. So I'm kind of pushing a line that the inferentialists are it seems difficult to if you're an inferentialist not to want to extend away just from the propositional or first order case to full dependent type theory. They're given in the same kind of pattern with these Fiek rules, and which have the category theoretic adjunctions to underlie them, and they're adjoints to very basic operations of our everyday discourse. this context extension. And they're things that, when restricted in the type terms of the type constructions, yield very, very basic logical operations. So why not take the unrestricted constructions as themselves logical? I think one way to think about this, I mean, you might worry we've strayed beyond the logical already, but I mean, for Brandom, we're just trying to make explicit the inferential relations that articulate the semantic contents of the concepts expressed by the use of ordinary non-logical vocabulary. And I'm claiming these things are already there and implicit in the way. So we've made them explicit now, things that were implicit in our everyday ways of going about things. Because something he's particularly keen on, the sort of end of this next list, the bit that's to do with conducting inference, asserting things, and then having people challenge your assertions, and then having people accept your statements. But before we even got there, we're involved in the game of asking for information and understanding. If you request information from me, I better understand what you're saying. And how are these questions themselves formed? Okay, well, my claim is that when you're posing questions to people, you're not just presenting them with propositions. You're posing more for them. You're setting things up in the form of types, I would claim. So, just think what happens to make sense of what's going on. So you hear somebody say, which fruit are ripe today? And somebody comes back with, blackberries, cherries, and wolves. And you, whoa, wait. Something's gone wrong here. And if you make explicit your sense of what's gone wrong here, you're kind of naturally inclined to think there's a type error. Wolves don't belong to the type of fruit. Something has gone wrong here. And even I might not even make sense of the question, which fruit were caudate yesterday? What are you on about? Caudate's not a predicate that applies to fruit. This sort of type checking error and puzzlement, I think, requires the language of type. So I think we're making explicit things that we already do in our ordinary inferential practice of exchanging information. Which fits nicely. So Arne Ranter wrote a nice book in 1994, trying to do a type-theoretic grammar, where he puts ordinary language into dependent type-theoretic terms. And he has a section where he's dealing with questions, and he's wondering about what form do questions take. And his one categorization he gives is, well, sometimes they are just somebody says proposition and then puts a question mark on the end. And sometimes they kind of look like this. They're P or Q, and you've got to tell me which one. And sometimes they're kind of who or what or which or where. And then they look a little bit like this. There's some sort of dependency going on, which fruit is in season or something of that sort, for some proposition depending on or there could be some kind of iteration going on. But if you think about it long enough, in some sense, really, they're all of them can be put into that form. They're all posing to you something like a dependent type. Some kind of dependent sum, and they're asking for maybe in context where there's just a single answer, there's a single element, there's only one A, which is B, maybe, and they're asking you for that element. But then in more general terms, I mean, we ask all the time for multiple elements. We say, right, tell me, guys, what are the options we've got before us? Which restaurant could we go to tonight? Yeah. Or the Doomsday Book, exactly the question that William asked, who lives here and what are their possessions? They're asking for the dependent sum. Which fruit are ripe now? How can I share these items fairly? We're asking for, we're not necessarily sort of single elements of singleton types, but just types in general. And I think this chimes in with a challenge that somebody's made to Brandom, that he's a little bit too caught up with the sentences, the propositions are already in place, and actually he owes us an explanation of how those propositions themselves are formed. Okay, and my claim is that often when you actually see how a sentence, if you understand how a sentence has been formed, it's gone via some types. So, for example, we know from we're going to do in dependent type theory, sort of Martin Luff dependent type theory, when we have two elements of a type, little a, b, of type A, it's reasonable for us to ask, is A equal to B, which will be cashed out. We won't be able to cash it out in propositional logic, but in first order logic, this will just amount to S equals T for two terms. Of course, from the perspective of Hott and other theories, we can even ask things about types. Is A equal to B as a type? And again, I can tell you a story, a nice phi x story, an adjunction story about the construction of identity types. Okay, but again, it's there very much. I can give you an expressivist account. You know, two scouts come back to you and they tell you, well, the first one tells you about a certain stranger and the second one tells you about a certain stranger. It's very natural for me to wonder if that's the same person, or are we being kind of invaded by at least two people? Okay, and I don't go across the types. I don't say, I wonder if that stranger is 5 or blue or whatever. These are two people, two terms of the same type people, and I want to know if the identity holds there. Oh, similarly, if I have guests to stay, I might even boot it up a little bit and ask, well, do I have enough beds to host them for the night? So I'm wondering about these types. Are they isomorphic as sets? Does guest equal bed? And you might be able to provide me. Oh, I can put them this way. Oh no, but that person snores. They don't want to be next to that one. And then I might rethink the isomorphism I want to use. You can go off and, if you want even higher, if you want to go the full hot way, you with gauge theory, you might want higher gauge of gauges and so on. We might want a homotopy type there. But why else? I mean, why aren't these things list type constructors? Why can't I see these as logical in a sense? When I'm providing you with an answer to the options before you, I give you a bunch of answers which form a list. They certainly come with the fiat rules, the constructors and the eliminators and so on and so forth. And I can give you a kind of expressivist account of how it makes sense of my inferential practice. And what about the truncation one, propositional truncation? So if you have a type A, it's really useful for you to form the bracket type, the one that essentially it's going to, if the type's empty, it's going to generate sort of falsity, and if it's not empty, it's going to give you true, the inhabited proposition. And a lot of the time, that's all I want. Is the house occupied? And you go on waffling on, yeah, X lives here and Y does, and maybe Z. I don't know. I don't care. Right, it's occupied. That's end of story. That's all I want to know. Okay, so this is part of our inferential story. Yet again, we get the fiat rules and we get truncation as left adjoint to this, that, and the other. And we're using it all the time. When I might have precisely, I don't care. I just want to know if I got enough beds for my guests. I don't care about the matching up at the moment. We can worry about that later. Essentially, I'm saying, do we have the right number of beds for the guests? Okay, so those so far have come the constructions that allow type formation processes where we've already been given a type and we're wondering about constructing a new type from them. There are presuppositionless types in our system, and the empty type and the unit type might be considered. I mean, the empty type, again, we've got nice formation, introduction rules, elimination rules, and so on and so forth. For the empty type, we've got the nice fiat rules these can be understood category theoretically in terms of adjoints. Now to these functors, again, I mean, they're appearing, of course, in the intuitionist implication. If that was logical, then you can see why the empty type there is, could be conceived as logical. And again, I mean, it's very useful in our inferential practice. We use it all the time. Which of our allies has come to support us? Well, none has. Who are the occupants of the house? No one, and so forth. And once you've got the empty type, well, then there's no difficulty getting the type, with the unit type, just by implication. Again, fiat rules and all that, and so forth. But yeah, once you allow me list, and once you allow me one, then you allow me the natural numbers. And then you can start to think, well, where do I start? What point was something not? Where did it go from being logical to going to be mathematical? I can raise that kind of question. And maybe these were part, in some sense, the lower levels of this sort of material was part of our inferential practice in some sense. Okay, yeah, I didn't realize I didn't have a great deal of time. Let me just finish off very briefly then. So if you allow me identity types and list type and products and co-products and dependent pair and all this, and 0 and 1 and the Booleans, if they're logical, well, these were all inductive types, and you might then think, why can't I have any of them? That bracket type or the truncation type was a higher inductive type. And once you've allowed me those, well, we got we've got everything. We've got synthetic algebraic topology, all that stuff they do, using hot to prove results in algebraic topology. And the boundary then between maths and logic seems to be immensely blurred at that point. Just to finish with a final construction. So if you take that context extension and the two adjoints, the dependent product and the dependent sum, and you you form the monad, the monad and co-monad from those things. These act very much like modal operators. So that the first one is very much acting like a necessity operator. And if you think about it, it's very much capturing invariance under variation over A. Okay. Whereas the second one is talking about possibility. If you take this type A to be like a collection of worlds, a type of worlds, it's very much the philosopher's notion of possibility as something going on in a possible world, or something necessarily happening in all possible worlds. So in which case, I think one can make sense of our modal uses of necessity and possibility, as I mean they would fit then very neatly as logical in this sense. And of course you can I don't believe, like some philosophers do, in some single type of possible worlds. I can allow this variation to take place all over the shop, and yeah, I can kind of cash it out in terms of various other things that you can connect through to temporal. I can have variation over time and so on and so forth. Good. Okay, so yeah, I've obviously taken up my full 30 minutes. Sorry for that. So yeah, the thrust of this dependent type theory is a kind of logic I'm claiming. You can see this on inferential grounds, the Fiat rules and the adjunctions. But I think in expressivist terms too, it feels like it's making explicit a bunch of things that are just implicit in our everyday inferential practices. And then once you go along these lines, it really starts to blur the line, I think, between the logical and the mathematical. And you could even claim there is no such line. So thanks very much. Thank you.
Thank you very much, David. Let's thank our speaker. Alrighty. Are there any questions? It does not look like we have any questions so far. No one on Zoom. Oh, sure. John has a question.
Do you think there's a reason for drawing the line between the logical and the mathematical in this story, or do you think that's just sort of a thing people do that's not?
Yeah, I mean, there's a long history of trying to do that. I mean, another approach to extracting the logical was that task. Well, people attribute it to Tarski. There's a student of Hermann Weyl called Mauntner who kind of got there first, which is looking at invariance under permutation. Yeah, and in some ways you can see, and I think Steve Audi wants to take that kind of approach and then understand Hott in those terms as this invariance under structural isomorphism, or equivalence, really. Yeah, and then it looks like, I mean, I remember asking Steve once, where does he now put the boundary? What does it do to it? And he says, well, it doesn't really exist anymore, does it? And I've got no stake in the game at all. I'm very happy for the whole thing. I don't need there to be a boundary between the logical and the mathematical. So yeah, I'm happy to see it gone. But then it's sort of philosophers have really relied on the thought that there was a distinction, so it should make their life a little trickier in some ways.
All right, thank you, David. And Jules, you raised the hand. Feel free to answer. Ask the question.
This might just be a slight also addendum to David's answer, because this is a pet interest of mine. But there's historically, like a big part of this debate was Hilbert on one side and Russell and others on the other side, and people like Frege, who had a kind of notion of mathematical terms versus logical terms. And oftentimes what was considered a logical term changed. For example, with Frege moving functions from being a non-logical term over to being a logical term. And interestingly, even people that were considered logicists like Carnap ended up coming down on Hilbert's side and saying, hey, we might as well have mathematical terms as part of our logics. And in many ways, Hott is a continuation of all of synthetic mathematics, and the whole Hilbertian tradition of axiomatic mathematics is all about basically dissolving the distinction, which essentially relies on a kind of metaphysical idea about, I don't know, primitive reasoning that might be suspect to certain people. But yeah, there's a whole lot of literature on it, and I'm a strong mathematics and logic are the same thing person, but the debate between Russell and Hilbert is like, yeah.
Thanks. Yeah, you can see, I mean, one line, I suppose, from the other point of view is you know, there's some special properties of first order logic, of course. I mean, you have completeness results after all. Yeah, but right, but where I still don't think that's enough to say, well, logic ends there. You know, so Quine's going to think, when the people are kind of pushing the boundary a bit, they're coming up with second order logic, and he famously says this is set theory in sheep's clothing. It's the wolf, it's the wolf of, it's gone beyond. And structurally there are differences, of course. As I said, there's the completeness results of first order logic, which aren't there for second order logic. But yeah, I don't have great deal of skin in the game of that. But you know, it's quite useful to look. There's some results from this interesting whole new world out here of people putting together these new foundational languages that maybe kind of ruffling the waters of things that you just assume to be the case. So I'm happy always to ruffle philosophers' waters.